So let's get to it. Let's fit a ResNet model to our data. First, we have defined the data set and check the previous notebook if you don't know how that works. And we have broken it down in training and validation to make sure that we are not overfitting, as we were mentioning before. Now we want to fit a model to our data, and we used to define models very simply for the linear models that we used in the previous simple example. We could just write down the equation, but we want to use a bit of a more complex deep learning model. We want to use a ResNet 50 model. You can read all of the ResNet model here. That was the winner of the, I think, 2015 ResNet ImageNet competition, and the paper is available for free online in arXiv. And you can read it here and learn all about its convolutional modules, which are very interesting and which have been responsible in large part for the revolution in deep learning, and are up to a point the reason why we are speaking about this today. We have this ResNet model that someone already implemented for us, and we can use it from the models library in PyTorch, and we just need to load it. Not only that, we load the structure of the model, and we also load its weights. Okay, so here we are effectively doing transfer learning. We are using some predefined weights for our model, for our ResNet 50 model. What weights are these? These are the weights that were created by training the ResNet 50 model with the ImageNet database. So essentially what we have here is a complex deep learning model that has been trained at image recognition and image classification of general things. The ImageNet database we saw has lots of classes of general images and includes things like the electric ray and the manta ray, but also people and houses and this kind of classes. Okay, so here we are loading the weights that can already do that, general image recognition, and we will retrain these weights, this model, this very deep learning model with 50 layers, to solve our problem of classifying subalpine bushes. Okay, and here you have quite a lot of detail of what training a model means, and the gradients again, and the different types of functions that can be used, and I recommend that you have a look at it, but I'm not going to stop at this today because I already did another notebook and you can read this on your own. But basically we want to fit our data to our model, and we will use the same training structure, the same training idea that we used for the simple models. We're going to have an iterative process. We are going to make predictions using the state of the model that we have at each step. Then we are going to compute the loss function that tells us how far the model is from our data. And we are going to compute, because we want to make this loss function as small as possible, we want to find the minimum value of the loss function, we are going to compute the gradients of this loss function using this backward. Then we are going to use the gradients that we have computed for the loss function and for all the parts of the model to create the next step, to change the parameters of the model towards a better loss function. Okay, and I was showing it from the very simple example that we did before, but the first approach that we do to the training function works just the same way. We have a forward pass where we make the predictions. We create a model, we pass the inputs that the data loader gives us. The data loader goes through our images and takes a number of images together with their labels and feeds the images to the ResNet 50 model and gets a series of outputs, gets a series of results. Okay, and then we compute the predictions of the labels with this from this running the data through the model. We compute the loss function between the target, the labels that we know are true for this training data, and the outputs, the predictions that we have just gotten. Okay, we need to reset the gradients at each step for technical reasons so as not to run into problems later. And at each point what we do is that we compute the gradient of the loss function. We want to minimize the loss function, we need to compute its gradients. As we are doing this, we are also computing all the gradients of all the nodes in the model, all the different parts of the model, and then we use those using optimizer step to create the new set of parameters for the next iterative step, and so forth, and so on and so forth. Okay, so this is the same structure that we had for the training function before in the simple example, and we have it here too. Differences, well, we used to compute the next parameters using by hand, let's say, using a simple calculation of gradient descent. Here we have an optimizer step, because this optimizer can be many different things, and we will be able to change them easily and to use any of the optimizers computed by the available in PyTorch. We are passing to this training model, to this training function, the model that we are using, the criterion, which basically is the loss function, the optimizer that we are using, and the data. And then a couple of technical things like the sizes and the device. And we will want to be running this always in the GPU. For the validation, we have a similar structure, but for the validation, we don't use the data to update the parameters. So basically, we do the predictions like we did, we compute the loss function, but because we also want to know whether our model is getting close to our validation data or not, and if it's not, then it means we are in trouble, we are overfitting probably, but we don't do optimization here in the validation step, because the validation set is not used for changing the parameter, just as this, let's say, safeguard for overfitting. We can simply make this a little bit more compact and do the two things at the same time, because we are always doing the forward step, we are always doing the prediction, so that's okay. And then if we are training, then we do the backward propagation and the optimization, and if we are validating, then we don't do it. Okay. Here we have a function that basically calls this training and validation function and takes care of storing the training loss and the validation loss each in the correct place. So it also takes into, it is the one that takes care of the number of epochs that are going to happen and so on. So I encourage you to have a look at this one, but basically this just calls nicely this function that's the important one, the training and validation function. Okay, and that's pretty much it. We can now put everything together, and we have data that we will read from somewhere, a folder named patches here. It will be used to build a PyTorch dataset. This dataset will be broken into a validation and a training and a validation dataset. Okay, and we will use the data loader class to pass that to PyTorch. We will put everything in CUDA, and then we will define our ResNet model and fit it using the optimized model function that we have just shown. Okay, as final steps here, we define the criterion, the loss function. We have decided to use one named gross entropy loss, but you can use any loss function that you like. Okay, we here send the model, the ResNet model that we have defined up here also from PyTorch, to the device, to the GPU that we are using, and then that's it. We have our data, we have our model, we have our loss function, we have our optimizer that we are also borrowing from PyTorch, Adamax in this case, but you can use any optimizer that you like, and then we can just begin training our deep learning model. And here it is. This is the training loop. In the optimize model function, you will see that we have done some pretty prints so that we can see how the process is starting, and we have some information. The size of the training data set is 1680 images. The validation data set is 419, 6 possible classes, and then we have the 5 epochs that we are going to run. You can change the number of epochs too if you want to. We report at each step the training loss and accuracy and the validation accuracy. Here we see, for example, that the training loss is decreasing, and we see that the training and validation accuracies are increasing, which is good. So our data is closer to our model, and our predictions keep getting more and more accurate. Here we have completed the 3rd epoch. Just I mentioned that the training values are not very informative by themselves, but that the accuracy values are a little bit more a little bit easier to interpret. Here, for example, we know that in the training set we are predicting 75% correctly in the 3rd epoch, and in the validation set 63%. Here we are seeing that the training accuracy is growing very fast, and the validation accuracy is not growing that fast, but it's still growing. So this is giving us an idea that the validation process is going very well. Maybe our data is not super representative. In the end, we finished with a training accuracy of 93%. So we were able to feed the model to the training data very well. The whole thing lasted a little bit less than 2 minutes, and the validation accuracy was not that super good, 60 something percent. So we can plot it here, and we see that the training loss goes down very precipitously, and the validation loss not so much. I'd say the accuracy grows very fast for training and not so fast for validation. So the most important thing, we have fed a ResNet 50 model to our Sapalpine bush data. So we have effectively used our first deep learning model from real data. Not only that, by defining training and validation, we are seeing that maybe the training process is very successful, the validation process maybe not so much. So maybe we are getting some overfitting here. We would need to go and get ourselves some testing data to see whether or not this deep learning model, this ResNet model, is really solving the general problem, if it has a good generalization power or not. As we mentioned before, because we used the ResNet model with pre-trained weights, and in this case we retrained all the weights of the network, we were able to use transfer learning from the ImageNet network. Okay? Even if we only achieved, in this case, what was it? 67% accuracy. This is a very, very complex problem. This is a problem in this case where we are using a relatively, let's say, classical deep learning network. ResNet 50 was was popularized in 2015, which in terms of deep learning is like prehistory, but it still was able to have a success of 67% in validation in classifying these 6 species of subalpine bushes. Is that a good result? Yes, it is. In some classification problems it may not be, but in this one, when we ask a bunch of humans, some experts, to classify these bushes in these same 6 species that we have trained a deep learning network to classify, okay, into these Matsu, Inutsue, Minakaeden, Nakamado, Kieraboko, and Sakura species, the best performance that a human observer was 55%. So this deep learning network that perhaps didn't have so good validation accuracy has had a result that's actually probably very good. We may be having some overfitting here. We will need more data, especially testing data, to see exactly what is going on. We have data from deciduous and evergreen bushes into different data collection missions that have slightly different characteristics, so probably this would merit quite a lot deeper study. But we were here to use a deep learning network to solve a real life problem, and we have been able to do it arguably better than humans could, than human experts could. Okay, stay tuned for other applications of deep learning networks to the analysis of drone images.